Hello, my name is Kritika Chakka, and I am presenting a paper titled Knowledge Graph Attention Network for Recommendation as a part of my project in Statistical Methods in AI and Machine Learning course for the spring 2022 semester. The success of recommendation system make it prevalent in web applications ranging from search engines, e-commerce to social media sites and news portals. Without exaggeration, almost every service that provides content to users is equipped with a recommendation system. To provide more accurate, diverse, and explainable recommendations, it is compulsory to go beyond modeling user-item interactions and take side information into account. Traditional methods like factorization machine cast it as a supervised learning problem, which assumes interaction as an independent instance with side information encoded. Due to overlook of relations among instances or items, like the director of a movie is also an actor of another movie. These methods are insufficient to distill the collaborative signal from collective behavior of users. So in this paper, the utility of knowledge graph, which breaks down the independent interaction assumption by linking items to their attributes is considered. It is argued that in such a hybrid structure of knowledge graph and user item graph, higher order relations which connect two items with one or more multiple linked attributes are an essential factor for successful recommendation. This is done by proposing a new method called Knowledge Graph Attention Network, or KGAT for short, which explicitly models the higher order connectivities in knowledge graph in an end-to-end fashion. All this will be clear once I explain a little more about what is going on in this paper. For now, this will be a high-level introduction. So how does this KGAT that we outlined here work? It recursively propagates the embeddings from a node's neighbors, which can be users, items, or attributes, to refine the node embeddings and employs an attention mechanism to discriminate the importance of neighbors. To predict user preference from key and widely available source of user behavior data, much research effort has been devoted to collaborative filtering. Now, what is collaborative filtering? We have a user X who needs recommendations, movies, to take an example. We find n multiple users who have the same likes and dislikes as user X. This set of users is called a neighborhood. The movies which are liked by these n users in the neighborhood are recommended to user X. Despite its effectiveness and universality, CF methods suffer from the inability of modeling side information such as item attributes, user profiles, and context, thus perform poorly in sparse situations where user and items have few interactions. Sparse situations are when, suppose, user X has not liked or rated any movies on Netflix. In that scenario, Netflix does not have any information about the likes and dislikes of user X. So, this is something which will be missing. To integrate such information, a common paradigm is to transform them into a generic feature vector through together with user ID and item ID and feed them into a supervised learning model to predict the score. Such a supervised learning paradigm for recommendation has been widely deployed in the industry, and some representative models include factorization machine, neural factorization machine, widen deep, and XDeep FM. We are going to later on compare our KGAT model with FM and neural FM to see how it does better. Now, although these models have provided strong performance, a deficiency is that they model each interaction as an independent data instance and do not consider them their relations. This makes them insufficient to distill attribute-based collaborative signal from the collective behavior of users. For example, take this figure here, which is a collaborative knowledge graph. U1 is the target user. Let me choose a better color. U1 is a target user to whom we have to provide recommendations. The yellow circle here and the gray circle here denote the important users and items discovered by the high order relation but are overlooked by traditional methods. High order relation is what KGAT adopts, whereas traditional methods are methods like supervised learning and collaborative filtering. There is an interaction, as we see in this figure, between user UI and movie, suppose I1, which is directed, suppose, by a person E1. Now, collaborative filtering methods focus on the history of similar users who also watched I1. So, those would be U4 and U5, while supervised learning methods emphasize the similar items with the attribute E1. That would be I2. Obviously, these two types of information not only are complementary for recommendation, but also form a high order relationship between a target user and item together. However, existing supervised learning methods fail to unify them and cannot take into account the higher order connectivity, such as the users in yellow who watched other movies directed by the same person E1, which are I3 and I4, or the items in the gray circle, which are I3 and I4, that share other common relations with E1. So, what is the solution to this problem? To address the limitation of feature-based supervised learning models that we saw above, a solution is to take the graph of item side information, which is also known as a knowledge graph, into account to construct the predictive model. We term the hybrid structure of knowledge graph and user item graph as collaborative knowledge graph (CKG). The key to successful recommendation is to fully exploit the high order relations in CKG. Example, long range connectivities. So essentially, the way to the yellow and gray circles are given as follows. You first go from user 1 to I1 and I1 to E1 using relations R1 and R2, and you go from E1 to I2 using relation R2 and I2 to user 2 and user 3. Wherever we are going against the arrow, you can take the negation of the relation. And to go to the gray circle, it will be similar. You go from user 1 to I1 and I1 to E1, and from E1 you are taken to I3 and I4 using these arrows. Now, to exploit such high order information, the challenges are that the nodes have high order relations with the target user increase dramatically with order size, which imposes computational overload to the model. And the higher order relations contribute unequally to prediction, which require the model to carefully weigh or select them. Now, several efforts have attempted to leverage the above CKG structure discussed for recommendation, which can be roughly categorized into two types: path-based and regularization-based. Now, path-based methods extract paths that carry the higher order information and feed them into the predictive model. To handle a large number of paths between two nodes, they have either applied path selection algorithm to select prominent paths or define meta path patterns to constrain the paths. Now, the issue with such two-stage methods is that the first stage of path selection has a large impact on the final performance, and the define but it is not optimized for the recommendation objective. Also, defining effective meta paths require domain knowledge, which can be rather labor intensive for complicated knowledge graphs with diverse types of relations and entities, since many of meta paths have to be defined to retain model fidelity. So, regularization-based models devise additional loss term that capture the knowledge graph to regularize the recommender model learning. Instead of directly plugging high-order relation into the model optimized for recommendation, these methods only encode them in an implicit manner. Due to the lack of explicit modeling, neither the long-range connectivities are guaranteed to be captured, nor the results of higher-order modeling are interpretable. So, what is the solution to this problem? Considering the limitations of existing solutions, we believe it is critical important to develop a model that can exploit high order information in knowledge graph in an efficient, explicit, and end-to-end manner. So, a new method named Knowledge Graph Attention Network is proposed, which has the potential of achieving the goal but has not been explored much for KG-based recommendation. So, KGAT is equipped with two designs to correspondingly address the challenges in high-order relation modeling. The first design is recursive embedding propagation, which updates a node's embeddings based on the embeddings of its neighbors. So the weight of the node essentially depends upon the weights of the neighbors of the node's neighbors. The second one is attention-based aggregation, which employs the neural attention mechanism to learn the weight of each neighbor during a propagation. Essentially, we are trying to learn what the weights of each of these neighbor nodes are, and we use a attention-based aggregation algorithm to do so. Now, how is this solution better than the already existing algorithms out there? Compared with path-based methods, it avoids the labor-intensive process of materializing paths, thus is more efficient and convenient to use. And compared to the regularization-based methods, it directly factors high-order relations into the predictive model. Thus, all related parameters are tailored for optimizing the recommendation objective. The next thing we look at are the advantages of KGAT. Conceptually, it is advantageous to existing KG-based recommendation methods, which either exploit the high-order relation by extracting paths or implicitly model them with regularization. We saw above here how KGAT is better than those two methods. Empirical results on three public benchmarks show that KGAT significantly outperforms state-of-the-art methods like Neural FM and RippleNet. Attention mechanism brings about interpretability benefits. That is, as we saw up here, it reveals the importance of neighbors in a higher order connectivity, and efficiency of embedding propagation for high order modeling is high in KGAT. The next thing we look at is task formulation. We introduce the concept of KGAT and highlight the high order connectivity among nodes. So the background information about graph concepts are needed, which are given here. The first thing we look at is the user item bipartite graph. In a recommendation scenario, we typically have historical user item interactions. For example, purchases, clicks, likes, etc. Here, we represent interaction data as a user item bipartite graph G1, which is defined as a relation between the user and item as follows. If there is a relationship between a user and item, user U and item I, then the value of that relation UI is equal to 1. Else, it will be 0. So in this particular graph, since there is a relationship or an interaction between user 1 and item 2, YU1 I2 will be 1. However, there is no interaction between user 1 and item 1, so YU1 I1 will be equal to 0. The next thing we look at is knowledge graph. In addition to interactions, we have side information for items, such as item attributes and external knowledge. Such auxiliary data consists of real-world entities and relations among them to profile an item. For example, a movie is defined by its director, cast, and genre. We organize the side information in the form of a knowledge graph G2, which is directed graph composed of subject, property, object, triple facts. So H would be the subject, R is the object, and R is the property, and T is the object. Formally, it is represented as shown in this expression, where each triplet describes that there is a relationship R from the head entity H to the tail entity T. For example, Hugh Jackman is actor of a movie called Logan. This is embedded into this expression as H taken for Hugh Jackman, R as the actor of, and T will be Logan. This states that the fact that Hugh Jackman is an actor of the movie Logan. Note that R contains relation in both the canonical direction, like in this example that we have taken of Hugh Jackman, R would be actor of, and in the reverse direction, that is acted by. Logan has been acted by Hugh Jackman. Moreover, we establish a set of item entity alignments where IE indicates that item I can be aligned with entity E in the knowledge graph. The next thing we look at is a collaborative knowledge graph. Here we define the concept of CKG, which encodes user behaviors and item knowledge as a unified relation graph. We first represent each user behavior as a triplet, U, interact, and I, where y_ui is equal to 1 is represented as an additional relation interact between user U and item I. Then based on the item entity alignment set, the user item graph can be seamlessly integrated with a knowledge graph. So essentially what we are doing is uniting G1 and G2 into a single graph G. G1 which we have seen here and G2 which we have here. Now, the entire task that we have discussed above has the following input and output. The input will be a collaborative knowledge graph G that includes the user item bipartite graph G1 and the knowledge graph G2. And the output is a prediction function that predicts the probability you had y hat of ui that user I would adopt item I. What is the percentage of adoption of user U to item I? The next thing we look at is what is higher order connectivity. Now, we have already discussed that exploiting higher order connectivity is of importance to perform high quality recommendation. Now, formally, we define the L order connectivity between nodes as a multi-hop relation path from E naught to EL, where any node in this path EL belongs to the set E prime, and any relation in this path RL belongs to the set R hat, and the Lth triplet will be defined as EL minus 1, comma RL and EL. That is, we define the two nodes and the edge between that node as a single triplet. And this sequence has a length of L. Now, to infer user preference, CF methods build upon behavior similarity among users, like we saw in the example with user X and its neighborhood users. Such intuition can be represented as behavior-based connectivity using the following expression, which suggests that user U1 would exhibit a preference on I2 because a similar user U2 has adopted item I2 before. And distinct from CF methods, supervised learning methods like FM and NFM focus on attribute-based connectivity, assuming that users tend to adopt items that share similar properties. For example, this relation shown here suggests that user U1 would adopt item I2 since it has the same director E1 with item I1 which she already liked before. However, FM and NFM treat entities as the values of individual feature fields. So they fail to reveal relatedness across fields and related instances. For example, in this relation, although E1 serves as a bridge connecting between the director I1 and actor I2, this is not modeled by a supervised learning model. We therefore argue that these methods do not fully explore the higher order connectivity and leave compositional high order relations untouched. So the next thing we see is the methodology. How does the proposed KGAT work and how does it overcome all of the challenges that we described above? This figure here shows the model framework, which consists of three main components. The first one is the embedding layer, which parameterizes each node as a vector by preserving the structure of the CKG. The next one is the attentive embedding propagation layers, which recursively propagates embeddings from a node's neighbor to update its representation and employ knowledge-aware attention mechanism to learn the weight of each neighbor during a propagation. The last one is a prediction layer, which aggregates the representation of a user and an item from all the propagation layers and outputs the predicted matching score in the form of this vector shown here. The next thing we see is an embedding layer. Knowledge graph embedding is an effective way to parameterize entities and relations as vector representations while preserving the graph structure. Here, trans-R embedding is employed, which is a widely used method on CKG. The trans-R method embeds each entity and relation by optimizing the translation principle, which can be written as EH of R plus ER will be approximately equal to ET of R. Now, EH of R and ET of R are the entity spaces H and T projected onto the relation space, making it HR and TR. Here, EH and ET belong to a set called R of D, and ER belongs to a set called R of K, and these are embeddings for H, T, and R respectively. For a given triplet H, R, and T, its plausibility score or the energy score is formulated as given in this formula here, where WR is a belonging to RKXD. And this is a transformation matrix of relation R, which projects entities from dimension D entity space into the K dimension relation space. So a lower score of this G or energy score suggests that the triplet is more likely to be true, and a higher G score suggests that the triplet is less likely to be true. Also, the training of trans-R considers the relative order between valid triplets and broken ones to encourage their discrimination through a pairwise ranking loss, which is given by LKG. Here, a set T, which includes this quadruplet HRT and T hash, is formed by using an already existing triplet HRT which belongs to G and forming a new triplet HRT hat T prime which does not belong to T, which does not belong to G. HRT prime is formed by replacing one entity in a valid triplet randomly. Also, sigma here is the sigmoid function that is widely known. This layer models the entities and relations on the granularity of triplets, working as a regularizer and injection the direct connections into representations and thus increasing the model representation ability. Next, we build upon the architecture of graph convolution network to recursively propagate embeddings along high-order connectivity. Moreover, by exploiting the idea of graph attenuation network, we generate attentive weights of cascaded propagations to reveal the importance of such connectivity. Here, we start by describing a single layer which consists of three components: information propagation, knowledge-aware attention, and information aggregation, and then discuss how to generalize it into multiple layers. So the first topic that we look at is information propagation. One entity can be involved in multiple triplets, serving as the bridge connecting two triplets and propagation information. Now, taking the relation E1, R2, I2, R1, U2, and the relation E2, R3, I2, R1, and U2 as an example. Item I2 takes attributes E1 and E2 as inputs to enrich its own features and then contributes user U2's preference, which can be simulated by propagating information from E1 to U2. Similarly, it also enriches its own information by taking information from E2 and giving better recommendations for U2. Now, considering an entity H, we use NH, which is in this format to denote the set of triplets where H is the head entity, and this is termed as the ego network. This is the expression for a ego network where pi hr of t controls the decay factor of each propagation on the edge h, r, t, indicating how much information being propagated from tail to head is conditioned to relation R. The next thing we look at is knowledge-aware attention. Now, we implement pi of HRT we saw above via a relational attention mechanism, which is given here, where we select tan H as the nonlinear activation function. This makes the attention score dependent on the distance between EH and ET in the relation R's space. Example, propagating more information for closer entities and less information for farther entities. And also, we employ only inner product on these relations for simplicity and leave the further exploration of the attention module as a future work of this paper. Hereafter, normalizing the coefficient across all triplets connected with H by is done by adopting the softmax function, which is given here. So, as a result of this, the final attention score is capable of suggesting which neighbor nodes should be given more attention to capture collaborative signals. While performing propagation forward, the attention flow suggests parts of the data to focus on, which can be treated as explanations behind the recommendation. The final phase to this is the information aggregation phase, where we have to aggregate the entity representation EH and its ego network ENH as the new representation of entity H. More formally, this is the expression we are trying to achieve. We implement F using three types of aggregators. The first one is a GCN aggregator, where the aggregator sums two representation up and applies a nonlinear transformation called leaky ReLU, which is a common transformation in Python. The next aggregator is a graph sage aggregator, which concatenates two representations followed by a nonlinear transformation. The last type of aggregator is a bi-interaction aggregator, which is carefully designed to consider two kinds of feature interactions between the entity representation EH and its ego network En of H. Here, W1 and W2 belong to the set Rd prime into D, which are the trainable weight matrices, and the dot here denotes element-wise product. Now, this is different from the above two methods GCN and GraphSage because we additionally encode the feature interaction between E EH and ENH. This term makes the information being propagated sensitive to the affinity between the entity and its ego network, like passing more messages for similar entities and passing less messages from dissimilar entities. To summarize, the advantage of embedding propagation layer lies in explicitly exploiting the first order connectivity information to relate user, item, and knowledge entity representations. The next thing we look at is high order propagation. We can further stack more propagation layers to explore the high order connectivity information. All the procedures that we saw until now have only the first order information aggregated, but as we stack more layers, we can get higher order information. Now, the gathering of this information is propagated by a high hop between neighbors. More formally, the nth step is recursively formulated using an entity by this expression given here, where the same function that we used above in a bi-interaction aggregator is used here to represent the propagation factor of an entity. Also, the information propagated within a L-ego network for the entity H is defined as follows. Here, there are L layers and to the ego network ENH. Using this process, high-order connectivity, which connects many users, items using different relations, can be captured in the embedding propagation process. Furthermore, the information from U2 in this relation that I'm writing down here is explicitly encoded in the term EU1 of 3, which says that the entity of U1 has a third hop neighbor U2 and its information is contained in this entire term. Clearly, the high-order embedding propagation seamlessly injects the attribute-based collaborative signal into the representation learning process. Now, the next thing we look at is how model prediction is done. After performing L layers of this high order propagation, we obtain multiple representations for user node U, namely a set EU of 1 all the way till EU of L for the Lth layer, and Also, analogous item node I has the set ei of 1 all the way till ei of L. As the output of the Lth layer is the message aggregation of the tree structure depth of L rooted at U as shown in figure 1, which is here. The output in different layers emphasize the connectivity information of different orders. So we adopt the layer aggregation mechanism to concatenate, which is here, the representation at each step into a single vector using this expression for U and this expression for I, where this double bar is a concatenation operator. By doing so, we are not only enriching the initial embeddings by performing the embedding propagation operations, but also allow controlling the strength of propagation by adjusting L. Finally, an inner product of user and item representation is taken so as to get the matching score. Now, how do we optimize this above model? To optimize the recommendation model, we opt for the BPR loss. It assumes that the observed interaction, which indicate more user preference, should be assigned higher prediction values than unobserved ones. So here, LCF is given by this expression where O has a set of U, I, and J in which U and I belong to relations that are observed, and U and J are relations which are unobserved and are a sample set produced. Sigma is a sigmoid function that is widely known. Finally, we have the objective function to learn equations. This is a generic machine learning function where theta are given these values, and E is the embedding table for all entities and relations. L2 is a regularization parameter parameterized by this entire term, which is used to prevent regularization. The next thing we look at is how training is done for this model. We optimize LKG and LCF alternatively in this equation here, where mini batch Adam is adopted to optimize the embedding loss and the prediction loss. Adam is a widely used optimizer which is able to adaptively control the learning rate with respect to the absolute value of the gradient. In particular, for a batch of randomly sampled sets H, R, T, and T prime, we update the embeddings for all nodes. Hereafter, we sample a batch of Uij sets randomly, retrieve their representation after L steps of propagation, and then update the model parameters by using the gradient of prediction loss. Now that we have seen how the model is trained, let's see what the complex time complexity analysis for the entire KGAT algorithm looks like. In an alternative optimization strategy, the time cost mainly comes from two parts. The first part is for the knowledge graph embedding, and the next part is for the attention embedding propagation. So the two complexities are given as follows. For the final prediction layer, only the inner product is conducted, for which the time cost for the whole training epoch is given as follows. So the time complexity analysis for the KGAT algorithm is a sum of the first, second, and third equations. The next thing we see are the different experiments that are conducted to evaluate the algorithm. In these experiments, the objectives of evaluation are how KGAT performs compared with state-of-the-art knowledge-aware recommendation methods. How do different components like knowledge graph embedding, attention mechanism, and aggregator selection affect KGAT? And can KGAT provide reasonable explanation about user preference towards items? The next thing that we see is the description of the data sets that have been chosen in the paper. To evaluate the effectiveness of KGAT, three benchmark data sets, which are Amazon Book, Last.fm, and Yelp 2018, are taken, and these are publicly accessible, vary in terms of domain size and sparsity. Now, the Amazon Book 2 is a Amazon review, which is widely used data set for product recommendation. To ensure the quality of this data set, the 10 core setting is used, that is, retain users and items with at least 10 interactions. In the last FM3, this is a music listening data set collected from last.fm online music systems. Herein, the tracks are viewed as items, and in particular, the subset of the data set where the timestamp is from January 2015 to June 2015 is taken. The same 10 core setting which is used here is also used in last FM3. The last data set is the Yelp 2018. This data set is adopted from the 2018 edition of the Yelp Challenge. Here, the local businesses like restaurants and bars are viewed as items. Similarly, the 10 core setting is used to ensure that each user and item have at least 10 interactions. To ensure the quality of the data set and retaining users and items with at least 10 interactions, a certain amount of pre-processing is done to the data. Besides this user item interactions, the item knowledge for each dataset also needs to be constructed. For the Amazon book and the last FM dataset, map items into freebase entities via title matching if there is a mapping available. As given in this table here, for each dataset, the number of users, items, and interactions are listed, and the corresponding knowledge graph has entities, relations, and triplets. Distinct from existing knowledge-aware dataset that provide only one-hop entities of items, the triplets that involve two-hop neighbor entities of items are also taken into consideration. For Yelp 2018, extract Extracting item knowledge from the local business information network, like category, location, and attribute, is done as a knowledge graph. To ensure this knowledge graph's quality, pre-processing the knowledge graph in three parts is done by filtering out infrequent entities, that is lower than 10 in both datasets, and retaining the relations appearing in at least 50 triplets. The next thing that we see is the learning procedure. For each dataset, randomly select 80% of interaction history of user to constitute the training set and treat the remaining as the test set. So 80% will be the training set and 20% will be the test set. In this training set, 10% is taken as the validation set to tune the hyperparameters, and the rest of the 70% is used to train the model. For each observed user item interaction, it is treated as a positive instance and then conduct the negative sampling strategy to pair it with one negative item that the user did not consume before. Now, the next thing we see are the experimental settings. In experimental settings, evaluation metrics are the first topic that is covered. For each user in the test set, treat all the items that the user has not interacted with as a negative item. So suppose user 1 had an interaction with item 1 and item 4. These are termed as positive interactions. However, if it does not have an interaction with item I5, then that is termed as a negative interaction or negative item. Then model each method outputs the user preference score over all the items except the positive ones in the training set. So in this given above example, the positive items are I1 and I4. So our model does not give a prediction score for these items. But since item I5 is not a positive interaction or a positive item, a prediction score is given for item I5. To evaluate the effectiveness of the top care recommendations and preference ranking, two widely used evaluation protocols are adopted, which are recall and NDCG. By default, in this algorithm, K is set to 20 and the average metrics for all users in the test set are reported using both these protocols above. Now that we know the procedure of how KGAT works and all the experimental setup, let us see how it performs when compared to already existing algorithms. The first thing that is reported is the performance of all the methods, and then each of the modeling of high order connectivity and sparsity issues are investigated separately. The performance result comparisons given in table 2 have the following observations. KGAT performs consistently better on all the data sets as observed here. KGAT improves this over the strongest baselines with respect to recall at 20 by 8.95% in the Amazon book dataset, 4.93% in the last FM dataset, and 7.18% in the Yelp 2018 dataset. By stacking multiple attentive embedding propagation layers, KGAT is capable of exploring the high order connectivity in an explicit way so as to capture collaborative signal efficiently. This verifies the significance of capturing collaborative signal to transfer knowledge. Moreover, compared with GCMMC and KGAT justifies the effectiveness of the attention mechanism, simply specifying the attentive weights with respect to compositional semantic relations rather than fixed weights used in GCMC. Also, supervised learning methods like FM and NFM achieve better performance than CFKG and CKE in most cases. As we see here in lines 1 and 2 are better than lines 3 and 4 in most cases, indicating that regularization based methods might not make full use of item knowledge. In particular, to enrich the representation of an item, FM and NFM exploit the embeddings of its connected entities, while CFKG and CKE only use that of its aligned entities. Also, the cross features in FM and NFM actually serve as the second order connectivity between users and entities, whereas CFKG and CKE model connectivity on the granularity of triplets, leaving high order connectivity untouched. Now, compared to FM, the performance of RippleNet verifies that incorporating two-hop neighboring items is important to enrich user representations. It therefore points to the positive effect of modeling the high-order connectivity or neighbors. However, RippleNet slightly underperforms NFM in Amazon Book and Last.fm while performing better in Yelp 2018 as we see here. The rest of the table can be interpreted similarly. The next thing we look at is a performance comparison with respect to interaction sparsity levels. Now, one motivation to exploiting a knowledge graph is to elevate the sparsity issue, which usually limits the expressiveness of recommender systems. Now, it is hard to establish all optimal representations for inactive users with few interactions. So here, in this experiment, it is investigated whether exploiting connectivity information helps elevate this issue. In these figures, the results with respect to the NDCG protocol on different user groups is given for all three datasets. Taking the Amazon book data example, the interaction number per users are divided into different groups so that the different groups have the same total interactions. This is done on the test set. Here we see that KGAT is the pink line in all of these graphs. And we see that KGAT performs way better than any other algorithm that we have taken for comparison in all three data sets, except for this point right here. So The better performance of KGAT signifies higher order connectivity modeling, which contains the lower order connectivity used in baselines and enriches the representations of inactive users via recursive embedding propagation. Also, it is important to note that the one possible reason for this negative effect is that higher order connectivity can introduce more noise into the user's performance, which is why we see this negative dip. The next thing that we see in this presentation is the deep insights on the attentive embedding propagation layer of KGAT and the impact it has. The first thing we see is the effect of the embedding propagation layer number L, which is how many neighbors that we consider while we try to get information. Here we see the more the number of layers, the better is the predicted value. The next table shows the impact of aggregators. Here we have considered all three aggregators that were defined in the above slides, and we see that the bi-interaction aggregator provides the best results. So this verifies that incorporating additional feature interaction can improve the representation learning, and also it illustrates the rationality and effectiveness of the bi-interaction aggregator. The last table shows the effect of the knowledge graph embedding and the attention mechanism. This is done to verify the impact of knowledge graph embedding by considering the three variants of just KGAT1, and the different layers here are the knowledge base, knowledge graph embedding and attention mechanism, just the knowledge graph embedding and just the attention mechanism. We see that the results are best when we have all three of them embedded in them, but removing knowledge graph embedding and attention components degrades the model's performance. So this part consistently underperforms when compared to these two parts. It makes sense because this fails to explicitly model the representation related to the granularity of triplets. Also, it is noteworthy that in comparison to the last setting, the second setting works better in most cases. One possible reason is that treating all neighbors equally might introduce noise and mislead the embedding propagation process. This verifies the substantial influence of graph attention mechanism. Now, the conclusions to this work is given as follows. We explore high-order connectivity with semantic relations in CKG for knowledge-aware recommendation. Also, a new framework called KGAT is devised, which explicitly models high-order connectivity in CKG in an end-to-end fashion. This work also explores the potential of graph neural networks in recommendations and represents an initial attempt to exploit structural knowledge with information propagation mechanisms. Besides knowledge graph, many other structural information indeed exists in the real-world scenarios, such as social networks and item contexts. For example, by integrating social network with CKG, we can investigate how social influence affects the recommendation. Another exciting direction is the integration of information propagation and decision process, which opens up research possibilities of explainable recommendation. This is the end of this paper presentation. Thank you.